Hi, I'm Elliot Rouse. I'm a professor at the University of Michigan, and today we're going to talk about modeling brushless motors in the context of the development and design of high-performance robotic systems. Before we get started, I'd like to tell you a little bit about my research group, the Neurobionics Lab, where first and foremost we study basic biomechanical science. And what I mean by that is we study joint mechanical impedance and how it's regulated by the nervous system during locomotion, but we also study perception and psychophysics and user preference and their role in wearable robotic systems. We also build wearable robotic hardware like exoskeletons and robotic prostheses. And what I think is special about our approach is that we pursue these two areas in parallel and they feed back on each other. So the fundamental science questions that we answer helps us build better wearable robotic systems, and our novel wearable robotic systems help us answer new fundamental science questions. But in this talk, I'm not going to talk about my research. This is a little bit of a different talk. This talk is going to be a tutorial on brushless motor modeling, and it stems from experience that we've developed in my lab over the past 5 to 10 years. I want to begin by telling you a little bit about who this tutorial video is for, and it's intended for researchers who design lightweight autonomous robots. These researchers, myself included, typically have a design process by which they evaluate motors. That usually includes assessing the current and voltage required. And these analyses are especially important for people who care a lot about the mass of their actuators. They don't want the actuator mass to be any larger than it needs to be, so we go through a set of reasonably detailed analyses. And I also want to say that this analysis or tutorial video is very high level and brief. And it's the subject of an upcoming tutorial article that will be much more in depth, and I'll mention that again at the end. And I also wanted to list some assumptions associated with this analysis, the most important being that there's kind of three-phase sinusoidally varying back EMF profiles, and that the field-oriented control commutation is in phase with the rotor, and we'll kind of talk more about what that means in a few minutes. There are countless technologies that have been developed using brushless motors, and modeling their performance is important, especially beforehand during the design selection process. It's one of the ways we know if a motor is properly matched to the design. If the motor isn't properly matched, the system could overheat, not reach the performance specifications desired. And the way we assess whether a motor is properly matched to its application is using a couple different ways. One is to look at the motor winding current and voltage and make sure it's within the permissible range in addition to its torque and velocity. And then we also would investigate how hot the motor gets, or its thermal temperature rise. We use this information to guide the selection of, for example, brushless motor drives that have to commutate these motors, in addition to bus, power supply requirements, how much current or voltage is required. And these factors are especially important for autonomous wearable robots or autonomous robots that have to carry their actuation and power supplies. So we want to make sure these systems are very efficient, or as efficient as they can be. And we want to make sure they're not carrying actuator mass that's not being used. To model brushless motors, we need parameters. We need the motor's torque constant, its winding resistance, its winding inductance, and this information is important for understanding the current and voltage demands on the windings for a specific application. To get these parameters, we typically use motor datasheets, but there are challenges. The constants described in motor datasheets are often ambiguous with respect to certain currents or voltages that are being referenced. For example, the motor's torque constant, it's often undescribed, sort of what current that motor torque constant is in relation to. That makes it difficult to model the motor's expected torque. In addition, the winding type is not usually provided. We'll talk more about that later. And oftentimes the motor kV number is the only number provided. So we're going to begin this tutorial on discussing the fundamental equations for both brushed and brushless motors. We'll review two common errors that I've noticed, and we'll conclude with an example. Our goal is to model the electromechanical dynamics of a brushless motor, and our approach is to reduce the three-phase brushless currents and voltages that exist into a single-phased brushed equivalent motor. That's defined by the Q-axis representation we'll talk about in a minute. To that end, let's begin by understanding the equations that govern ideal brushed motor operation. The first equation is governed by Newton's second law and describes a relationship between the applied torques and the angular acceleration of the rotor. The second equation is Kirchhoff's voltage law, which says that the drop in voltages around the winding resistance will be equal to 0. And we do this reduction to this brushed motor analog because it becomes convenient and easy to assess. Our goal is to model the three-phase currents and voltages that exist in brushless motors as this single-phased brushed equivalent motor that's helpful for making design decisions. We begin by borrowing the Q and D axes of field-oriented control, and without going into too much detail, the Q and D axes are orthogonal axes that rotate alongside the motor's rotor, so they're pinned to the motor's rotor. The Q axis is the torque-producing axis. So the Q axis becomes the single dimension that represents this brushed equivalent motor. And the D axis is non-torque producing. So any current on the D axis does not produce torque, but it does produce loss. And off-the-shelf field-oriented control-based brushless motor drives keep the current on the D axis equal to 0 as a constraint under normal operating conditions. The two equations that now govern this brushed equivalent motor on the Q axis are shown here. There's two things I want to highlight. The first is that the voltage drop across the winding resistance is proportional to the phase resistance. And secondly, that the voltage drop across the winding inductance is proportional to an effective inductance. We'll talk more about those later. Usage of the Q axis allows for convenient trigonometric simplifications to be made. And what's most helpful is that it becomes a DC representation, just like the brushed DC model. And to give you a little context about where we are kind of in this design process, you would typically have the angular velocity and torque requirements for your application. But in order to solve these equations, you need the motor's parameters again. So you need the phase resistance, Q-axis torque constant, this effective inductance, and maybe the Q-axis back EMF constant. So our goal here again is to quantify the Q-axis voltage and current, which we can use in the design process. To use the information provided on motor datasheets, we often need the motor's winding type. There are two types of brushless motor winding types, delta and Y, with Y being the most common by far. This information is usually obscured or not included on motor datasheets. So there's a couple different ways to obtain the motor winding type. An easy way is just by inspection to see if you can actually see the node of the center of the Y. That's usually a dead giveaway. But another way to tell motor winding type is to use thermal imaging, also by inspection. To give you a little bit of an example of kind of what that looks like, here's a thermal test where we ran 8 amps through 2 leads of a T-motor U8, and we just heated the windings up and we watched the pattern, the thermal pattern that existed. And because we see 2 warm windings and 1 set of hot windings, that means this motor is delta wound, where if we saw 2 hot windings and 1 cold winding, that would mean the motor was Y wound. Following the determination of motor winding type, we need to determine the inductance and resistance coefficients to use in our Q-axis voltage and current model. And the way that we obtain those values is using motor data sheets or by directly reading terminal measurements. Terminal measurements or line-to-line measurements are measurements that are made across any two of the 3 motor leads. The equations that govern the phase resistance and effective inductance are shown, and these can be converted directly from the line-to-line measurements of resistance and inductance. At this point, we almost have all the parameters needed to use our Q-axis representation of this brushed motor analog. We have the equivalent inductance and the phase resistance, which we can get from line-to-line measurements. And now we need the torque constant or the motor's back EMF constant. To get that, we're going to use the relationship that the back EMF constant on the Q-axis is going to be equivalent to the torque constant on the Q-axis, just like in a brushed motor. To measure these properties, we're going to set up a small experiment where we measure the line-to-line voltage, so that's the voltage across any 2 of the 3 motor leads, regardless of winding type. And we're going to measure this voltage as a function of rotor velocity. And as the rotor is spinned, it will induce a sinusoidal voltage profile, where the amplitude of that sinusoidal voltage profile we'll call V bar line to line. Using knowledge of the motor's winding type, we have representations or expressions that can convert the line-to-line amplitude of the back EMF voltage to the Q-axis back EMF constant. At the very end of this talk, I'll give a brief example where I walk through this calculation. At this point, we have all the coefficients obtained to model the Q-axis current and voltage, and we obtained these coefficients using terminal measurements, so measurements line to line, without even the requirement to need a motor's data sheet. The two equations that govern q-axis current and voltage are shown here from before. The way that we would solve these is by first solving the second equation, so Newton's second law, where we would numerically differentiate the expected rotor angle to predict or estimate the q-axis current, and then we would plug that into the top equation, Kirchhoff's voltage law, where we numerically differentiate the q-axis current and solve for the voltage, q-axis voltage. And these equations represent the fundamental relationships that govern brushless motor operation for high-performance robots. And it can be used, q-axis current and voltage can be used to make a number of important design decisions. It can also be used to calculate resistive power loss. This is a little bit outside the scope of this tutorial video, but the power loss, the Joule heating power loss, can be calculated as the q-axis current squared times the phase resistance. And we can use this q-axis current and phase resistance to predict the thermal temperature rise. What I'd like to do now is highlight two common errors that I've seen sort of in my own work and in the work of others. And one of those errors is the conversion of a motor's kV number directly to its torque constant without proper transformations. Common sort of drone-style motors are sometimes only provided from their manufacturer with a kV number, something like kV 100, and the determination of the motor's torque constant or back EMF constant is left up to the engineer. And what the kV number is actually describing is the amplitude of the line-to-line voltage as a function of rotor velocity. And we'll use the relationship that kV line to line, the amplitude of kV line to line, is 1 over the amplitude of the line-to-line back EMF constant. So the kV number is also called the motor's velocity constant. If we plug this equation into the equation for torque, we get a relationship that describes how kV line to line relates to the q-axis torque constant. And if we use this direct conversion of this kV number to the torque constant, we see an underestimation of the torque constant by a factor of the square root of 2 over 3 for delta wound motors, and it overestimates the torque constant by a factor of square root of 2 for Y wound motors. Another common error is the use of the terminal resistance to calculate the resistive power loss. Power loss is especially important because it governs how warm the motor is going to get or the predicted winding temp, which can be a design driving factor. Since the terminal resistance is commonly provided in motor datasheets, it's tempting to use this as the value when modeling or assessing your motor. But for modeling the q-axis voltage or modeling a single-phase representation of a brushless motor, we really need the phase resistance. For delta wound motors, in Y wound motors, we have relationships for how the line-to-line measurements convert to the phase measurements. And if we use those instead, we put power loss in terms of the line-to-line resistance, we can obtain the factors that affect power loss. So if the terminal resistance is used instead of the phase resistance, for delta wound motors, we would underestimate power loss by a factor of 2/3. And for Y wound motors, we would overestimate it by a factor of 2. And that overestimation of power loss by a factor of 2 can really change some decisions that are made. So this is a really important error that I've noticed. What I'd like to do now is an example where we determine the back EMF constant or the motor's torque constant from scratch, so from no information obtained from a motor's data sheet. The motor we're going to focus on is the T-motor U8, which is helpful to analyze because we have existing published characterization data. Something that's required for this analysis is the motor's winding type, which we obtain by thermally imaging it and obtaining the winding type as delta wound. Our strategy here is to use the line-to-line voltages to estimate the q-axis constants as mentioned before. And as a reminder, if we looked at the line-to-line back EMF that gets induced, it's sinusoidal with an amplitude of V bar line-to-line. And if we look at our equations for the line-to-line voltage, we can use the equation for a delta wound motor to predict the q-axis back EMF constant. So in order to do this, we need the line-to-line amplitude of the line-to-line back EMF voltage, and we need the motor's rotor velocity. So to do this test, we have a motor that's being driven by an electric drill at a constant velocity, and the motor is not connected to a drive. So we have the 3 leads exposed that are connected to a scope. If we spin the motor while connected to the oscilloscope, we can see the sinusoidally induced back EMF profile. If we zoom in on that oscilloscope screen, we can see a couple of things that matter for this calculation. The first is the frequency of that sine wave, which it says is 151.6 hertz, and we'll have to account for the 21 pole pairs in this motor. The next is the peak-to-peak line-to-line voltage, which is about 9.5 volts as I read it. A trick would be to use the RMS value, which can be reported from an oscilloscope or a voltmeter, and that might have a little more accuracy than trying to estimate the peak-to-peak voltage. But we'll use peak-to-peak voltage in this case. So to determine the Q-axis back EMF constant, we're going to use the amplitude of the line-to-line voltage in addition to the angular velocity of the rotor. The amplitude of the line-to-line voltage can be read directly off the scope. It's about 4.8 volts. We're going to divide that by square root 2 over 3. And then we have to convert the magnetic angular velocity, which is about 151.6 hertz, into the rotor velocity in radians per second. So we're going to multiply by 2 pi and then divide by 21 poles per rotation, which we get by counting the magnetic poles. And if we follow this equation out or compute the answer, we get 0.13 volt-seconds per radian as the Q-axis back EMF constant, which means the Q-axis torque constant is also 0.13 Newton meters per radian. If we compare these measurements to measurements that exist from our previously published literature, we can see a Q-axis torque constant obtained empirically that was about 0.14 Newton meters per amp. So our purely calculation-based, only from an oscilloscope measurement gave us 0.13, and our independent measurements using empirical measurements of torque provided a Q-axis torque constant about 0.14, so that agrees pretty well. I wanted to thank you for listening to this talk. This work was led by a PhD candidate in my research group named Eunhee Lee. He's done a great job. I also wanted to highlight an upcoming tutorial article that's been a group effort between myself and Eunhee, and then also many other researchers in the field. And it's much more in depth than this video. It's about maybe 10x more in depth. So thank you for attending, and I hope to see you around the conference.